All right, bom dia. All right, that is as much Portuguese as you're going to get out of me today. Good morning, everyone. My name is Aaron Stannard. I'm the founder and CEO of a company called Petabridge. So we are primarily a .NET shop. We support Akka.NET, which is a C# port of the Akka actor framework. So we basically help our customers build real-time distributed systems on top of actors. What we're going to be talking about today is something that we kind of do in addition to our open source work. We've actually developed a product designed to help our customers trace messages that are being processed through these big actor hierarchies using some standard open source technologies that we're going to be learning about today. So this whole area is called distributed tracing. And this is how companies like Google, Netflix, Amazon, and Twitter are troubleshooting production issues with their distributed systems and microservices. So the first thing that we're going to talk about today is microservices and some of the common people problems that they cause. So there's a lot of big benefits to using microservices, but there's some significant downsides that come into play as well. And one of the things we're going to learn about is how distributed tracing helps solve one of the most painful problems that distributed systems and microservices introduce. Then we're going to cover a little bit about how does distributed tracing work and what are some of the things as an application developer that you should understand about it in order to get the most value out of using it. And then we're going to talk a little bit about OpenTracing, which is a vendor-neutral standard. So this is really important for people who are building things like database drivers or web application frameworks or actor frameworks in my case. This is a way to go and support tracing inside your frameworks in a manner that doesn't force your end users to pick a specific tracing implementation. They can basically use anything that targets this standard. So we're going to learn a little bit about what that standard is, what are some of the terms it uses, and then I'm going to give a couple of demos using Zipkin, which is one of the popular open source OpenTracing implementations. And then we're going to finish up today by talking about some distributed tracing best practices for use inside your own applications. And then at the very end, we'll probably have some time to take some questions. So that's what we're going to cover today. So, microservices, I'm sure by now, are something you've heard about at least 100 times so far in the past 2 days here at QCon. So I don't think I need to explain what they are. The long and the short of it is, though, is that the way we've traditionally developed and deployed production applications is this sort of single process model, where you have a monolith where all of the code that does everything is all inside one code base and is deployed as one process. That's sort of been historically the way we've deployed software over the better part of 20, 30 years. Over the past, let's say, 6 to 7 years, we've started moving towards this distributed model, where we introduce process boundaries between different parts of our application in order to achieve a handful of benefits that are really important for scaling software organizations, more so than scaling the software itself. The primary reason why we've gone down the route of adopting microservices isn't because it's a better way to scale software. It's a better way to scale software developers, is why we go and do it. I can have a team of developers that work on my first service, and this team can have a fundamentally different composition than the second team that maintains another service, because service one might have things like a front end on it. So we need to have JavaScript developers and UI designers and people that you don't need for building a pure backend service like service number 2. Service number 3 leverages a database real heavily, so it might need to have a database administrator working on that team. And then you might have a common infrastructure team that kind of supports all the different service groups inside this organization. What microservices fundamentally give us is the ability to allow each of these teams to still build a complete and integrated product together, and the way we do that is through service contracts. If service 1 sends service 2 an input of type A, service 2 is guaranteed to send an output of type B or C back to service A. As long as those service-to-service contracts are versioned correctly and aren't broken on each deployment, we can go ahead and have each team release software on its own independent release cycle, using its own technology stack, and using its own tools. Microservices are really about designing large software organizations where you can have faster release times, you can fix small bugs more quickly, and you can even do things like change the internal implementation of a microservice without having unintended side effects on other services around it. So it's really about trying to give developers increased freedom and flexibility when it comes to technology choices and deployments. But there's a major cost that this breaking up of a monolith introduces, which is another category of people problems. The first major problem that we get is what's known as loss of coherence. For instance, if I'm an engineer working on Google search, and every single search request an end user submits through the UI actually hits 25 different microservices in order to get the final result. And that final result includes ads, it includes translations, it includes all sorts of different content. As a Google engineer working on the front part of that service, the part that touches the end user, I may not be able to explain what actually happens when a request starts and when a request finishes in the middle there, because those implementation details are now hidden from me. That's part of the idea behind microservices in the first place. But where this can really start to cause a problem is what happens if something goes wrong in the process of trying to fulfill that end user request? Where do I start looking to try to troubleshoot this issue? Most of our processing tools for doing things like monitoring and logging are all designed to tell a story about how well our application works in production from the point of view of a single process. All of the context, all of the source code, all of the data is all there running inside one monolithic process. That's historically the model our monitoring tools have adopted. That model completely breaks once we introduce process boundaries and microservices. So if I'm in service 1 and I depend on service 2, and service 2 depends on service 3, and service 3 depends on a database, if I'm sitting here trying to maintain a high quality of service in service 1, and I start getting timeouts back, who do I yell at? Is there something wrong with my service? Is there something wrong with service 2? Is there something wrong with service 3? Or maybe was there a database failure that affected service 3? And the answer is the errors can actually happen in more than one place simultaneously. But we don't really have an easy way of knowing that, because the information we get back when something does fail is usually just a cryptic error message and a status code. We lose a lot of the data that we would have had if we were running inside a monolith, such as a stack trace and other bits of data. We can't attach a step-through debugger to a distributed microservice and debug it that way. A lot of the tools and techniques we've learned as developers don't scale very well when it comes to trying to troubleshoot these problems. And the reason why this is that microservices lend themselves to information silos. All of the data about why one microservice failed might be self-contained inside a bunch of logs that aren't correlated to any of the other services that use it. So we have no way of really figuring out which request in microservice 2 which response from microservice 2 corresponds to which request from microservice 1. So the process of trying to debug even basic problems in a microservice environment becomes very labor intensive. You have to get a developer from each team that was involved in that potential failure and start doing things like manually correlating logs and monitoring metrics together. It takes a process that one developer could do independently by themselves and turns it into a group project. And you know how much developers love meetings, right? So microservices lend themselves to debugging by committee is the biggest problem that they have. And it's like the worst possible form of pair programming on the planet, where every developer is trying to figure out which of the other two in the room screwed up. So this is actually a real people problem, and it gets worse the more microservices and the larger your organization is. All right. So how do we go about solving this problem? The answer is we need to come up with a way of telling stories about how well our applications worked at runtime from the point of view of multiple processes rather than one process. This is where distributed tracing comes into play. So tracing itself is not a new concept. It's been around since the 1970s. The new innovation here is let's have a way to take the context from all these different requests that were all sort of issued as part of trying to fulfill one logical end user operation. And let's correlate all of the logs, all of the metadata, and even some of the stack trace together into one place. So rather than having a bunch of developers yelling at each other in a conference room, someone can just go and get that data from a web dashboard like this. What you're looking at here, this is a screenshot of a Zipkin dashboard, which is one of the distributed tracing engines we're going to talk about today. What you can see, if you go ahead and step through here real quick, I'm going to grab my mouse. So we have here a set of traces. Each distributed trace itself is the sum of, in this case, this first trace on screen here, is the sum of 8 logical operations. Each operation is recorded with what's called a span. And don't worry, I'm going to introduce the terminology and go through it in a moment. But I can see here, this operation took 44 milliseconds. There were 8 spans. And you can't see the address very well on the big screen here. But I can basically see that there were 2 distinct services involved in this operation. In this operation down here, I can see that there were 3 spans. That took about 25 milliseconds for this operation to run. And this involved 3 services. Already, can you see how just illustrating the relationships between those requests this way is like a giant leap forward in terms of understanding what actually happened in the course of processing a request? We haven't even dug into the detailed data yet. But just on the surface, we already have the ability to kind of follow the propagation of requests inside our system. And in a little bit, I'm going to pull up a live demo and show you some of the types of data that Zipkin can capture. But this is sort of the first part here, distributed tracing. Now here's the core features that make distributed tracing valuable. And bear in mind, the resource we're trying to conserve with distributed tracing is developer time. We're trying to make developers more productive and make it so we can fix bugs more quickly and locate the sources of error more accurately. That's the idea. The first really big innovation of distributed tracing is the idea of preserving trace context across requests. So when service 1 calls service 2, it's going to forward a little bit of information about the current trace that's being executed. That way, any of the trace data that's recorded by service number 2 can be correlated back together again, and we can get a histogram like we were looking at earlier. So that's the first big feature of any distributed tracing engine, is this correlation capability. Next is the ability to gather really detailed information about each individual operation. And these operations can be occurring concurrently, and they're definitely occurring asynchronously over the network somewhere. We can capture things like log messages, or we can capture metadata in the form of tags. So for instance, one type of tag you might use in the course of doing a distributed trace would be something like the status code you got back from whatever the downstream service was. Or maybe you'd go and record something like the user agent property that from the user who issued the HTTP request. And you can actually search on that metadata inside a system like Zipkin. You can go ahead and filter, I want to see all the users who had this error, who are using this version of Chrome, or this version of Firefox, etc. The other really big feature that makes distributed tracing systems useful is what's called out-of-band reporting. And I'm going to illustrate that specifically in the next diagram. But what this means is the order in which operations are being executed inside your microservice architecture isn't going to be predictable, typically. Therefore, one operation might start and finish at a later time than another operation finished and started. We need the ability to go and report on all these finished operations back to our tracing engine independently. Otherwise, it'd be a giant coordination problem that would be really awful to solve. All of these distributed tracing backends like Jaeger and Zipkin and Datadog and all that stuff solve this problem for you by allowing out-of-band reporting. You can go and report traces whenever they complete, and Zipkin will go ahead and construct that timeline for you in the order in which they were completed. So it's able to go ahead and do all that sort of asynchronously. And of course, no tracing system would be all that complete without the ability to actually see the trace. So that's the last big feature that distributed tracing systems introduce, is diagnostic tools and the ability to filter and search for different traces inside your system. Now, bear in mind that these distributed tracing engines were developed by fairly large internet companies. So Zipkin was developed by Twitter originally. Jaeger was developed by Uber. They're used to handling, global scale type operations. So a lot of these tracing tools have the ability to export their data to other analysis systems like Apache Spark or Elasticsearch. So the little web UI that I'm showing you for our demo today, that's not the end of the story. If you want to have someone from your data science team try to do some correlation between, let's say, 99th percentile latency and a certain error rate, you could do that type of analysis with a Spark job or something like that. These distributed tracing systems are designed to make that easy. Now, the process of actually collecting a distributed trace looks a little bit like this. We have this microservice architecture where we have this, we're kind of just going with a linear request pipeline here. I'm not going to do any crazy fan-out type stuff or anything like that. Client comes in, sends a request to web service number 1. Web service number 1 is going to call a second web service. That's going to call a third web service, is going to query a database. Well, this is what out-of-band reporting is going to look like. The first span we might report back to Zipkin is going to be the database query being completed. That's one discrete operation that we are going to want to profile independently from our HTTP requests. So that operation is going to finish first because none of these responses can be propagated back upstream before it's done. So we complete that operation. We're going to go ahead and record it. Service number 3 is going to complete its HTTP request first, so we're going to record it. Service number 2 is going to complete its operation next, so we're going to record it. And then finally, we're going to go ahead and record the initial span that started everything, which is service number 1. When service number 1 completes its span, that's when we send the final output back to the end user. So span number 1 is going to be the longest running span out of all the ones that we capture here. So there's a few pieces of information that are worth bearing in mind about these distributed traces. First is the trace ID. The trace ID is designed, and by the way, these are things your tracing driver will do for you, but I just want you to understand how the concept works. The trace ID is what determines which of all these, which operations are all related to each other. The span ID identifies each discrete operation as it occurs. And then the third thing you're seeing there is what's called the operation name. This is the human-friendly name that you're going to be using to query and analyze your data. The span and trace IDs are for the benefit of your tracing system to correlate stuff together. And here's what the output of that trace might look like. So you can see here, the first, and by the way, from left to right is the passage of time. So think of this like a histogram. Span number 1, this service1.http.myop, is the first operation to begin. That operation is going to kick off service2.http, this little internal operation there. So that's sort of like a downstream span. Third operation that we're going to kick off is in the third service down there. And then we're going to see that we have a database query that runs in the middle there. That database query finishes, and then service 3's HTTP call finishes, then service 2 and service 1. Well, what sort of data can we grok just by looking at this? Well, first is, if you're a performance architect trying to improve response times in your application, we can see the bottleneck is probably going to be service number 3 right here by the looks of it. Service number 2 takes 180 milliseconds, but 140 milliseconds of that is waiting on service number 3. The total end-to-end trip time is 210 milliseconds, but the lion's share of that is still going to be waiting on service number 3. So if I were an engineer working on service number 1, and I want to try to improve my end-to-end performance, that's probably going to look like talking to some of the developers on service number 3 and understanding why this took so long. Why did service number 3 take 100 milliseconds on top of a 40 millisecond database request to do its job? Was it inefficiently paging through the results set to get back? Are we querying way more data than we need, and therefore we're having to perform a lot of unnecessary serialization? Those are the sorts of questions you can start to ask now that you have this data that clarifies that for you. Make sense to everyone? Yeah. So these are the types of things distributed tracing allows us to do clearly. So one of my favorite expressions I use when I'm working with either one of our open source teams or working with employees is I'll say, like, win arguments with data. That's exactly what distributed tracing is designed to allow you to do, is go ahead and have a clear picture of what actually happened and be able to go through and line by line identify the different operations that occurred inside your system. Now, like I mentioned, there's lots of different popular tracing implementations. You're not limited to like 1 or 2 technologies here. I only put 3 up on the slide, but there's like at least 10 tracing implementations that all implement the OpenTracing standard. Jaeger and Zipkin are like the 2 biggest open source implementations that I'm aware of. But there's also proprietary products that offer additional features and reporting, like Datadog, for instance. So if your CTO wants to do distributed tracing but wants some flexibility and options, being able to go, there's a lot to choose from. So you can go through and pick one that sort of best suits your organization's needs. And what's really nice about the way the distributed tracing ecosystem is evolving is there's an open standard that most of these vendors are targeting, which gives library maintainers like myself the ability to go ahead and support whatever your preferred tracing tool is on the back end. As you can imagine, tracing is kind of an invasive thing inside your application. We need to be able to capture data from lots of different places inside your application to give you the most complete information you need for debugging. Therefore, there's going to be sort of an obvious need for standardization here, right? Let's say if if your company was a big Play framework user, and you wanted to use Datadog because that had some enterprise reporting features that your engineering leadership thought would be really useful. Well, if the people who wrote tracing integration for Play framework hard-coded everything against Zipkin, that'd be a massive problem, right? You'd essentially be locked into that tool. Even worse, what would happen if you used Play framework plus Couchbase, and Couchbase used Jaeger instead of Zipkin? Do you need to go ahead and maintain? If we start maintaining multiple different tracing systems, we're back to that exact same problem we were trying to solve before of data silos. So that's why the OpenTracing standard exists. It tries to define a common set of terms, so the same word means the same thing in every tracing system. It also exposes a common set of APIs that you as an application developer can use for recording traces. And it also provides a set of APIs that I, as a library developer, can use to make sure that whatever tracing implementation you use works with our framework. So we're trying to go ahead and give a greater degree of flexibility to end users ultimately. The other thing the OpenTracing standard defines is a standard way of propagating that information about trace context between your services. So we define like a standard serialization format for that. That's another important thing. So let's define some terms real quick, and then we'll eventually work our way to a little Zipkin demo. The first key term is what's a trace. In my opinion, the best way to think about it is a trace is an end-to-end operation inside your application. End user hits one of your services, gets a response back. Well, the process of fulfilling that end user's request might touch a whole bunch of different microservices potentially. That's okay. We're going to go ahead and record spans for each one of those operations that occurred in each one of your microservices. And we're going to stitch them all together into one congruent and coherent trace that any developer on your team can go and look at and figure out what exactly happened in order to fulfill that end user's request. That's what a trace is. As an end user of distributed tracing, most of what you're going to be looking at is recording spans. A span is a single logical operation that occurs inside your system. So you can think of it as, one HTTP, web method, that's going to produce one span. If that HTTP web method has to asynchronously query a database or call another service, those subsequent calls might produce additional spans, which all get correlated back together into that trace. So this raises another important concept about spans, which is that they have relationships. The most important relationship is parent-child spans. So a parent can have children. And what allows us to do is it shows the flow of execution. This request caused this request, which caused that request. Those are all like child relationships. And we'll see some examples of that when I do my demo in a moment. Next is this notion of span context. This is the information that you propagate between your microservices, is the span context data. So what's the ID of the current trace that this request belongs to? What's the ID of the parent span that kicked off this operation? This data is consumed by the tracer, which I'm going to pull up in a second, is consumed by the tracer to help pre-populate the next span that you're going to create for the next operation, to go and say, okay, this request is related to this one, and the span context is what defines that relationship. So the tracer is sort of the actual client that you're going to be using to go ahead and record your data and pass it back to something like Zipkin or Jaeger. And the tracer also is what's responsible for essentially being able to serialize and deserialize all of that span context data as it's propagated between your services. And I'm going to talk a little bit about what are some of the formats that tracers use for doing that. So we're going to cover that before we leave today. But this is where we're going. Now, this is probably a good time to start looking at a demo. This is what instrumenting a span might look like inside your application. Now, this syntax is C#, but we're not doing anything that's particularly, I'd say, idiomatic as far as C# goes here. So the iTracer interface is one of the OpenTracing interfaces for defining a tracer. And so in this case, I'm using a tracing library that my company built, which implements the OpenTracing standard. And we're going to be targeting a Zipkin, and we're going to be publishing data back to Zipkin using the HTTP transport. Different tracing engines might support different reporting mechanisms for publishing data back to the underlying tracer. So Zipkin supports HTTP, but it also supports Apache Kafka as one way of publishing data back. I think it also supports gRPC. So if you're operating at a really large scale like how Twitter does, you'd probably want to use Kafka for publishing data back upstream. So that's going to be less expensive on a per request basis than HTTP will. Anyway, that's implementation detail that's hidden from me when I'm instrumenting my code. Next, I have this concept here of a span builder. As the name implies, this is a builder interface you can use to sort of construct all of the metadata for a particular span. And here's a really cool part down here. Tracer.ActiveSpan. All of the open tracing libraries, and by the way, there's tracing libraries in virtually every language. So in terms of just like Zipkin alone, I believe it supports Go, Java, C#, Node.js, PHP, and I think there's even a C++ implementation being worked on. So it's available in lots of different languages and flavors. You don't have to worry about it not really supporting your runtime. But all of those runtimes, if they support open tracing, come with a tool that's known as what's called a scope manager. The job of the scope manager is to figure out what is the current active span for the operation you're processing right now. So what a lot of people do in production is they'll do something like inject some instrumentation into, let's say you're building an application with Node.js, and you're using the Express framework there. You'll introduce an HTTP pipeline handler that'll go ahead and create a new span automatically every time an HTTP request comes in. If you want to augment that span with either some additional child spans or maybe you want to tag on some additional metadata specific to your application, you can call tracer.activeSpan to get a reference to it. Make sense? So scope management's pretty useful. It's one of the best practices we're going to talk about. Down here, I'm going to go ahead and use my span builder to build a new span. I start by giving the span a human-friendly name. So this sort of describes the operation that we're doing. This is something that I might go and search for later. And then I'm applying some metadata to this span. So I'm using a tag to go ahead and add some searchable properties to it. Down here, I can check to see if the active span isn't null, I'm going to go ahead and declare the span I'm building as a child of the active span. So this child of property right here gives me the ability to go ahead and say, I'm related to this span, which is how we build those sort of little flowchart looking things inside Zipkin, is through these child relationships. Then I'm going to go ahead and start my span and finish it immediately in this case. So when you start the span, that's what starts the timer for how long the operation takes when you call that start method. When you call finish, that's when the timer closes and you can see how long the operation took. Pretty straightforward. Let's take a look at what some of this data actually looks like in a system like Zipkin. Let me pull that up real fast. All right. So this application right here is a really simple set of microservices I built on top of Akka.net. It's, as the name implies, it's a web crawler. And if I go and pull up my little command app down here, this is just running on like a local Docker cluster on my machine. I can see that we have 4 microservices. In fact, let me clear the screen real quick. So we have 4 microservices. A web UI, which is where the end user is going to submit a crawl request. A tracking service. This is what builds the index for a website we're going to crawl. And then the crawl service, which actually does all of the heavy lifting, does the downloading and parsing of web pages and all that stuff. All right. So what I'm going to do is I'm going to go ahead and start a crawl inside this application, and my tracing infrastructure is going to pipe all the messages that we sent between these services and trace them all back to Zipkin. And we'll be able to go and take a look at some of the data we captured when we do that. So let's fire this up. Go ahead and we'll go ahead and crawl one of our websites and see what happens. All right. All right, we're starting to download some pages now. That looks pretty good. And if I go to Zipkin here, the first thing, by the way, can everyone see the screen all right? Does the font need to be a little bigger or anything? Looks good in back? Thumbs up? All right, good. First thing you'll see here is a set of service names. So these service names are things, are properties that you set. Let me pull up my slides real fast. The service name is something I set right here, or I'm calling it demo app inside the source code. The service name that I'm using in my little production application here is the name of my microservice plus the address it's running on. So I can see the port number and the domain name that I'm using. So let's see, if I go and take a look. So I've ran this demo a few times without deleting and recreating the database here. So I've got some dead microservices that show up on that list. Let's find a live one. 44635, okay? So I'm going to go ahead and take a look at traces that hit this particular node. Let's see, web. I think it's this one, yeah. Next, I can go ahead and filter by the type of operation that ran. So these are the operation names that I was recording earlier. So I had spans named after these. So these are the names of actors inside my system. These could also be the names of methods that you invoke inside your application. They could be the HTTP route of a web, HTTP route inside your application. It could be whatever you want. It's kind of up to you to pick the convention you want to use. So I'm going to go and take a look at anything that hits SignalR. SignalR is a WebSocket library in C#. That's what that is. All right, let's find some traces. All right, so here we go. So look at this. We had what looks like one really long-running process compared to the others. This one took 355 milliseconds compared to 15, 70, etc. And I can change the sort order of how I view these spans if I want. I can go ahead and sort it by oldest first, newest first, etc. But this is showing me the longest running operations first. So let's take a look at what happened. So I can see these three operations are related to each other, and there was a huge amount of processing time between this first operation and the second one. If I dig in here, I can see that the type of message that was published was this publish stats tick operation, which actually occurs on a timer, this particular message. And I can see a log message that I recorded here. And okay, now it makes sense to me why this operation took longer than the others. This was us downloading the very first web page in the crawl. So in order for us to find more URLs to go and crawl, we have to download and parse this one first. So it's the longest running operation potentially. So we downloaded our first web page, and I can go ahead and see that log message get recorded here. And I can see, here's the URL, the actor recorded it. These are tags, by the way, is what I'm showing on screen here, all these values. I can see the type of message that we handled. I can see who sent the current message, and I can see the implementation type of my actor here as well. And I can see that this request originated on my web crawler crawl service node that does the downloading. I can see next that this request resulted in a crawl job stats message being sent to my tracking node. Next node further up, the next service further up the food chain. And I can see that we've more or less received sort of a similar log message to what we had before, pretty much the same data. But I can see that the message type is different. And I can actually see that this message was sent from a remote service down below here. And then finally, at the very end, I can see that my SignalR actor, the actor that finally publishes this output to the end user, received a job status update message from the sender of the previous message. So I can go and basically track the progression of how that piece of data was published using my distributed tracing engine like this. This is some of the metadata that you can collect using the sort of span and span builder keywords inside OpenTracing. And if I really want, I can go and export all this data in JSON format and run sort of additional queries and analysis on it. And I can also go ahead and tap directly into some of the APIs Zipkin exposes on the back end and analyze this data using Spark. In fact, the storage engine I'm using for my spans for this demo is actually Apache Cassandra on the back end. So I can go ahead and query that natively using Spark if I want to. And then if we take a look at some other little bits of data, let's just go ahead and search. What's the address of my tracking node here? Tracking node is 37403. Okay. Let me pull that up. Here it is. Find traces. So we can find some more complex operations in this case. Tracking node kind of sits in the middle of everything. Now if I take a look here, this communication only involves the crawler and the tracker. So this is probably an instruction to download a page that we haven't indexed yet. All right. And what you can see here, I'm not going to click all the way through it. What you can see in this case is operations being executed in parallel across multiple actors inside that other microservice. So in addition to supporting those very linear sort of request streams, you can also record fanouts where you gather data back together again, just like that. So that's kind of the crux of setting up, playing around with a tool like Zipkin, and this is how you collect data for it. One important thing that you as the end user are responsible for to some extent is the trace propagation. Inside each of your HTTP requests, or in my case, actor messages, I have to have some way of forwarding the current trace context to the next service downstream. So each of these requests right here between these services, I need to go and forward what was the ID of the span running on service 1 when I propagate this to service number 2. So that information needs to be forwarded and then extracted from that message somehow. And there's a couple ways of doing that. One of the standards that, and by the way, this is actually on the cusp of being a W3C standard. There's an RFC out for it right now. This is called B3 header propagation, and it was the Zipkin team who originally pioneered this. The way they go and encode this metadata is through these HTTP headers inside your application. So every time, let's say if you're working with Play Framework, what Play Framework would do is create a new span context object using one of the built-in APIs in OpenTracing. Every time it sees these headers available. And it would use that to go ahead and create a brand new active span that's a child of this span ID here. So this is how we can go and preserve that data over the wire. There's other carrier formats you can use. Like a really common one is a dictionary, where you basically just have, it's like a string dictionary, essentially, where the keys are these same records here, and the values are the same as well. And you'd pass that along as like a JSON object or something like that. So these are ways you propagate that tracing information between processes. So you can read up a little bit more on that when you start diving into actually working with it. But the last thing I want to finish up with before we take some questions about distributed tracing is talking about some best practices for actually using it inside your application. The first and most important one is immediately touches on what we just covered. Standardize on carrier formats inside your application. Make sure everyone uses the same tools for trying to figure out what the current trace is. If everyone does their own thing, you're going to have a bad time. So try to standardize on that early. In my applications with Akka.NET, I use those dictionary formats because we don't use HTTP, so we have no use for headers. But if you're doing a lot of HTTP-driven microservices, B3 headers are probably a good way to go. Next, introduce distributed tracing at the infrastructure level inside your application if you can. What I mean by that is, don't necessarily try to litter tracing stuff inside your application code if you can help it. If you can come up with a way of injecting, let's say, a trace capture engine inside your HTTP framework or inside your socket framework, or maybe you have a handler that sits in front of your message bus or something, try to inject it there in kind of an aspect-oriented way if you can. That way, a lot of the work's done for you. What you could do inside the application layer is augment some of that data with additional helpful properties if you want. Other good places to try to inject your tracing stuff, your logging system is another good place to try to inject it. And if you have, like, let's say a standard error handler routine, injecting it there is another good place to do it. So that way you basically don't have to just litter this code everywhere inside your application. Another one I would recommend is using the scope manager inside OpenTracing. There's lots of different scope manager implementations. So like the most common one in Java is the thread local scope manager, which basically pins an active scope to the current thread. That's really helpful. In C# we have what's called the async local scope manager, which uses async await to figure out in each context what the current scope is. This will make it a lot easier to automatically establish those parent-child relationships if you do that. So that's really helpful. Most OpenTracing implementations will automatically make any new spans you create children of the active span by default. So you don't even need to manually do that if you don't want to. So that's worth doing. And then, like I said at the very end here, having your logging infrastructure inject the data you're already capturing into those traces is super helpful. Essentially, what it can do is take all of the logs that occur independently on each service, and it'll put it all together into that histogram. Like you saw me do during my live demo a minute ago. That by itself is worth the entire value of doing distributed tracing. It eliminates the need to have that conference room meeting with 3 engineers where you're comparing log printouts and stuff. It's light years ahead of everything else. So that'll do it for my presentation today. I hope you've enjoyed it, and I'd love to take some questions from you. Thank you.
Great talk, man. Congratulations. Questões? Okay.
First, is there any cost, for example, when you introduce this kind of requests, and you have to send this info to this
performance costs?
Yes, or for example, what happens if in some of these of those span points, the server of the
like Zipkin goes
Zipkin
down.
goes down.
So that depends on the transport you use. So if you're using Kafka as your transport to Zipkin, it might have reliable delivery built into it. My HTTP driver, if I can't upload some spans to Zipkin, I just drop it in that case. The performance cost, because most of the span reporting happens asynchronously, it should occur out of band with your HTTP requests. The biggest performance cost probably isn't good. There's going to be some CPU utilization when we're serializing stuff and sending it out. The biggest cost is really going to be memory, though. Because as you notice, these trace objects aren't exactly small, some of them. Particularly if you're appending a lot of log messages to it. Those are big string objects, which tend to be most expensive from a memory footprint point of view. So what I would recommend that you do is do some memory profiling when you start firing this up. And a lot of tracing engines support things like sampling, where if it becomes too expensive to trace every request, you can say, let's trace 10% of our requests. That way you can throttle down the overhead it introduces. To answer your question? Good.
Thanks, man.
You're
Really
welcome.
nice presentation. When you have, for example, an event-driven architecture, do you have any kind of best practice or advice to use tracing to trace the messages in your architecture, in your application, instead of HTTP requests?
So, yes, like message-driven architectures.
Yeah.
All right. Yeah, so for a message-driven architecture, what I typically use is a strategy called envelopes, where I have an envelope that wraps the real message, and that envelope has the trace information on it. And then I usually, what I've kind of done with my product here is I'll have a base class that all of my message processors handle. Well, they'll take the envelope, they'll use that to reconstitute the current span context, and then they'll have their next span flow from that. So that's the strategy that I use. I guess other ways you could potentially do it, if you're not using envelopes, would be to have some optional property on the message itself that could have that data on there. But I think the envelope approach I like better because it kind of decouples your domain events from the infrastructure. Good. Go ahead.
First of all, thank you. Does this kind of tool substitutes aggregating log tools like Graylog, or they work in conjunction?
So his question was, if you're using a distributed tracing engine, do you still need like the elk stack and other log aggregation tools? I'd argue no, you probably don't need both. Because a lot of the same data you're already capturing from the logging system can be visualized in the tracing engine. Now, if there's some benefit you get from your logging engine that you can't easily get, let's say some really good dashboards you can set up in Logstash and Kibana, and you still want that, okay, then you could have both. I wouldn't be so prescriptive as to say you only ever need one of those things, but I would argue that a lot of the utility of a logging system is kind of superseded by what you get from this. Okay, good. I think we've got time for one more?
One more question.
One more question?
Uma questão mais, pessoal. Não? Dou-lhe uma, duas, três. Okay. Thank you very much.
All right. Thank you, everyone.